So this problem states calculate the time required to fly from point P to B, and point B is right here, and because it lies on the minor axis, and it wants us to find this in terms of eccentricity and period. So what is delta t? Well, we know that mean anomaly equals n times delta t, and that equals the eccentric anomaly minus e times sine of the eccentric anomaly, and n equals 2 pi over t, so let's substitute that, and we know that at the axis equals pi over 2, so substituting that in, we have this, and then rearranging for delta t solves to this. And then simplifying further, we know that sine of pi over 2 equals 1. And that's our answer. This problem states if the eccentricity of the elliptical orbit is 0.5, calculate in terms of the period, the time required to fly from P to B. So those are our knowns. We're trying to find delta t. We know that mean anomaly equals this expression. And we know that we're at 90 degrees, so E is 90 degrees, but we know that in order to use this equation, we need to use radians by pi over 2. So never plug the degrees into this equation. And so we're plugging in pi over 2 and the eccentricity. And that's equal to 1, so that simplifies this. We know that mean anomaly equals n times t, and rearranging for t, we get m over n, and we know that n equals 2 pi over t. So plugging in what we found for mean anomaly, we get the time in terms of t, the period. So that's the change in time to get from P to B in terms of the period. We have an Earth orbiting satellite which has a period of 14 hours and a perigee radius of 10,000 kilometers at time t equals 10 hours after perigee passage. Determine the radial position, the speed, the radial component of the velocity. So right now I wrote out the time in seconds, and mu is this for Earth. So now we're finding the radial position, so we can use the conic equation. However, we don't know A, E, and theta, but we do have enough information to find all of those. So we know that the period is 14 hours, so we can rearrange that equation for the semi-major axis A. And then plugging in, we get that the period equals, or the semi-major axis equals this. And we also know that the semi-major axis is equal to that, so we can rearrange for the radius of apogee. And since we know the radius of perigee and we just found the semi-major axis, we can solve this. And we know that the eccentricity equals this. And now all we need to do is find theta. Even though we don't know where this spacecraft is, so we don't know what the eccentric anomaly, capital E, is, we do know the rest of the values, so we can plug all those in, simplify, and use Newton's method to solve for the eccentric anomaly. So we find that E equals 3.9915 radians. And then we can use this tangent equation in order to find theta from the value of the eccentric anomaly, capital E. And since we're using the tangent equation, we do not need to do a quadrant check. If we were using the sine and cosine equations, we would have to do a quadrant check. So that's just rearranging right there for theta. And then plugging everything in, we get 203.11 degrees. And remember that E needs to be put into that equation in radians, and then you convert to degrees. So now we're using the conic equation. Because we just found what theta is, we solved for E and A. So now we can find that the radial position is 42,000, about 42,000 kilometers. So now that we found our radial position, we can use the vis-a-vis equation to find our velocity at that location. And now we need the semi-major axis, which we already found right there, so we can plug that in. So it's about 2.3 kilometers per second. And now we need the radial component of the velocity, so it should be less than 2.3. So in order to use the radial equation, the radial velocity equation, we need to know the angular momentum, so we can solve for it right there. And now we can solve for the radial velocity, because we already found what E and theta are. And if you're plugging it in using degrees, obviously make sure to put your calculator in degrees. Okay, the satellite is in Earth's orbit, has a perigee and apogee radii of this, respectively, and find its true anomaly 40 minutes after passing the true anomaly of 80 degrees. So we're finding the eccentricity right here and the semi-major axis. And now we're finding the eccentric anomaly, the initial eccentric anomaly before time passes. And it equals this. So we know that the initial mean anomaly is equal to this. Plugging everything in, we get that equals that. And then we know that the mean anomaly after that amount of time that passes is equal to the initial one plus n delta t. And then plugging in all that we know how long it has passed, so we can find what the new mean anomaly is. Now we need to know what the eccentric anomaly is, and since we know what the mean anomaly is, and we know the eccentricity, we can use Newton's method in MATLAB to find that it equals this. And then converting eccentric anomaly into the true anomaly, we can use the tangent equation, rearranged for theta, and no quadrant check is needed. And we find that it equals this in degrees. Thanks for watching, and subscribe for more useful content.